Katie Miller, and today we are going to be talking about the variance of air pressure and temperature with altitude. So as we change the altitude, what happens to the pressure and the temperature? So today, while we go through these equations, we're going to be working with a few assumptions. So one of them is that we have 1 mole of gas. This means when we use the ideal gas law, the N for number of moles can just be 1, and it makes the math a lot simpler. The second assumption is that this is an adiabatic system, which means that there is no heat change. And the third assumption is that this is reversible, which means that the internal and external pressure are equal. So we're going to start out with a couple of equations that I'm going to write down, and these are going to be our basis for our deriving of the formulas as we go on. So I'm going to erase this. Our first equation is dP over dz is equal to negative rho g. So the negative rho, it kind of looks like a P, but it's not a P. That is going to be our density of the gas that we're looking at. The second equation is du is equal to delta Q minus P dV. So this delta Q is going to be the heat change, and as I said before, this is adiabatic, so there is no heat change. So once we see this again in a little bit, this will end up being 0. Next one is the ideal gas law, PV equals nRT, and again, as I said before, we're working with 1 mole of gas, so this N will be 1, so we can just read it as PV equals RT. The third one is going to be fourth one is going to be CV is equal to dQ over dt. So CV is the specific heat at a constant volume. And we're also going to be working with CP, which is the specific heat at a constant pressure, which is equal to CV plus R. So these are our basic equations that we're going to be working with. And I'm going to erase the other ones, and we're going to focus on the first one. So the first thing that we want to do is we want to replace the density with the values that we know in the ideal gas law. So this is going to end up dP over dz equals negative m, and the m stands for the molar mass of the gas that we're working with, negative m p over RT times G. And so now that we have this, we're going to want to get the T and the P on one side of the equation. So we're going to multiply by T over P. That means these cancel out. And we have to do that on both sides, so we end up with T over P dP. We're also going to move this dz over to this side, so that we have just the dP with the P and the dz on this side, equals negative mg over r dz. So now that we have this, we're going to take the integral of both sides. So we're just going to write that there and write that there. So this is going to be from P1 to P2. This is going to be from Z1 to Z2. And this integral is pretty easy to do. It ends up being negative mg delta z over r equals, and we're going to keep this in the integral form, so P1 to P2 T over P dP. So this is the first main equation that we're running into. So this we are going to save for later, and we are going to use it once we solve for the temperature. So I'm just going to erase it. And now we're going to start out with the second equation that I mentioned, which is du equals delta Q minus P dV. Now, as I said before, this delta Q, that is just going to be 0. There is no heat change. We can just write it as 0. And now we're going to do the same thing that we did before with rho, and we're going to use the ideal gas law to replace P with what we know it is from the ideal gas law. So that's going to be du is equal to negative RT over V dV. And so now we're going to use a little algebra, and that we're going to change du into CV dt. CV dt is going to be the same thing as du, so that's going to be equal to negative RT over V dV. So now that we're here, we want to move the temperature over to the other side to get it with dt. So we're going to have CV over T dt equals negative R over V dV. Now if you look at this, you can integrate both of these sides very easily. So if we take the integral from T1 to T2 because it's with respect to T, and then V1 to V2 because this side is with respect to V, these integrals are very easy. It ends up being, we can take these constants out, and it ends up being the integral of 1 over T dt, and the same on this side but for V, and you end up getting CV times the natural log of T2 over T1 is equal to negative R natural log of V2 over V1. So now that we have this, we're going to use a property of a natural log to move this CV over to this side, and we're going to end up with natural log of T2 over T1 is equal to natural log of V2 over V1 to the negative R over CV. So now we've moved both of these constants to an exponent, and now that we've done that, we can use another property of natural logs to get T over T1 equal to V over V1, all of that to negative R over CV. So now that we have this, we want to get temperature in terms of pressure. So that means that we want to replace this V with something that we know is pressure. So we want to get T over T1. We're going to use an ideal gas law for this. We're going to get T over T1 is equal to RT over P, all of that over RT1 over P1, and all of this is still to the power of negative R over CV. So as you can see from this, both of these R's, they cancel out. But these T's and P's don't cancel out because this is T1 and T, P1 and P. So now we're going to combine our like terms. So we're going to have T over T1 is going to equal T over T1 times P1 over P, and that is going to be negative R over CV. So now we're going to combine a little bit more, and we're going to end up with T over T1, all of that to the R over CV plus 1 is equal to P over P1, and all of this is still going to be to the R over CV. Now this is where we get to a point where we can replace the exponents with Cp over Cv, which is a ratio of the specific heats, and we are going to call that gamma. So I'm going to erase the board, and we're going to replace that R over Cv with gamma. So we're going to end up having T over T1, all of that to gamma, is equal to P over P1, and all of this is going to be to the gamma minus 1. And so we're going to use a little bit more properties of exponents, and we're going to get T over T1 is equal to P over P1, all of that to gamma minus 1 over gamma. And so now we're going to want to get this T all by itself. So we're going to move the T1 over, so we get T equals T1 times P over P1, all of that to the gamma minus 1 over gamma. So now we have this equation. This is the second equation that we've run into, the second important one. And we're going to use this with the first equation, and we're going to substitute it in so we can get our pressure equation. So I'm going to erase it so I have room. So we ended up with T equals T1 times P over P1, all that to the gamma minus 1 over gamma. And remember that first equation that we had was the integral P1 to P2 of T over P times dP is equal to negative mg delta z over r. So now that we have this, we're going to take this t and we are going to substitute it into the equation. So we're going to end up with integral from P1 to P2 with T1 times P over P1 to the gamma minus 1 over gamma, all of that over P, dP equals negative mg delta z over r. So now what we're going to do is we are going to take out the constants. So we're going to have T1 times P1 to the gamma minus 1 over gamma times the integral of P from P1 to P2, the integral of P to the gamma minus 1 over gamma. And that is all going to be minus 1. And then we are going to take the integral of this, and this is still equal to this value, but I'm not going to write it out right now because we're going to work with this integral. So now that we have this integral, it's pretty easy to solve. We're going to end up with P delta minus 1 over delta, all of that, I'm sorry, that's gamma. Gamma minus 1 over gamma. And we are going to have that from P1 to P2. And so when you do this, you're going to end up with P2 gamma minus 1 over gamma minus P1 to the gamma minus 1 over gamma, all of that divided by gamma minus 1 over gamma. And so this is still multiplied by this, T1 times P1 to the gamma minus 1 over gamma, and it is equal to negative mg delta z over r. So now we're going to move this and this over to this side. So we're going to end up with P2 gamma minus 1 over gamma minus P1 gamma minus 1 over gamma is equal to negative mg delta z over r times T1 times P1 to the gamma minus 1 over gamma times gamma minus 1 over gamma. And so now that we have this, we can see that this term and this term are alike, so we can combine those. And when we do that, we're going to have P2 to the gamma minus 1 over gamma is equal to P to the P1 to the gamma minus 1 over gamma times 1 minus mg delta z over r times T1 times gamma minus 1 over gamma. And so now we use another property of exponents, and we end up with P2 is equal to P1 times 1 minus mg delta z over r times T1 times delta, or gamma minus 1 over gamma. And all of this is going to be to the gamma over gamma minus 1. And so this is going to be our pressure formula. So as you can see in this formula, the only thing that is changing is the delta z. All of the rest are constants or numbers, and this means that we can use this to find our temperature equation. So as we saw before, T equals T1 times P over P1, all of that to the gamma minus 1 over gamma. So now we're just going to substitute in our pressure. So we're going to have T is equal to T1 times what we got before, 1 minus mg delta z over over R, multiply that by gamma minus 1 over gamma, and this is going to be your temperature formula. So we have an equation for our pressure, and we have an equation for our temperature. So going through all of these steps was a little confusing, but after a little bit of time, it ends up making a lot of sense, and with our assumptions, it simplifies it enough so that we can get these two pretty easily. And so now we know how the pressure and temperature of air changes with a change in altitude.